So we're now going to introduce the number e and natural logarithms. Now, first of all, every one of these is an exponential, and each of these exponentials has got a different base. We can choose any base we like, really. We can choose decimals, fractions, we can choose 10, 7, 2, 3.5, or we can have an unknown base for base of a, whatever that is. Well, there's also a very specific base which is used quite often, which is the number e, which is another irrational number like pi. The number e is 2.718. To 3 decimal places, it actually just keeps on going after that, on and on and on, like pi does. So I'll talk a little bit more about why it's an important number later, but first of all, let's do some calculations with it. If you're asked to find e to the power of 7, this means 2.718 to the power of 7, but we're not going to type in 2.718 to the power of 7. We're going to use a calculator instead. So if you grab your calculator, in the top right corner, there'll be an e square somewhere, and usually it is just above what looks like in, but is actually ln, and we'll come to that later. So you might have to press Shift ln, and you'll get the e. E of 7, I'm going to grab a calculator and I'll see what I get. So to find out what e to the power of 7 is, I've grabbed my calculator. I'm going to find where ln is on my calculator, usually on the top right of most calculators. I'm going to press Shift ln, I can see there's an e there, ex, and I'm going to put 7 in, and I get the answer, 1096. I'm going to round to 2 decimal places, 0.63. Okay, let's pick another one. I'm going to find e to the power of minus 3. Exactly the same idea. Shift ln, or whatever is on your calculator, minus 3, and I get the answer, 0.05 to 2 decimal places again. Okay, so I'm now going to So I've got a couple of exponential equations to solve, both of them this time involving the number e, 2.718. So we're going to use exactly the same technique as when I solved previous exponential equations, which is think of solving for x, get the x on its own, so I want to remove everything else, and I'm going to use change side, change sign. So I'm going to grab this exponential to the base e, I'm going to move it across, so the x is going to be left here, it's actually going to drop down and become a regular x. And the opposite of an exponential base e, well, that is a log to the base e of 5. However, you may or may not find log e on your calculator. You could type in log and then manually put in the letter of the value e. However, we don't want to do that. What we want to use instead is the other name for log to the base e. It's got its very own name, which is ln, and it's also got its very own key in the calculator. So log to the base e of 5 is actually just ln 5. You can call this natural log of 5, you could call it ln 5, some people even just call it ln 5. So we're going to type in the calculator and we should get the answer 1.61. So now onto our second, slightly trickier exponential equation using e. We're going to solve for t, so we want to get t on its own, and we want to basically take this exponential across, but we can't do that until the whole of the left hand side is an exponential. This 4 isn't part of the exponential. So we're going to grab this 4, take it across. What's going to be different about this question is lots of decimal work that we're going to be careful with. So I'm going to do 7 divided by 4. E to the minus 2t is 7 divided by 4. Now it's 1.75. Now what I would say is if you get a long decimal number, maybe leave in 3 or even 4 decimal places. Don't round it too much until the very end of the question. If you round too early, you can lose quite a lot of accuracy here. So 1.75 was actually my full answer there. So now I can grab this e and I can move it across, and the opposite of a exponential base e, minus 2t drops here, is a natural log, or an ln. So minus 2t is, and I'll put ln 1.75 in, 0.56. Finally, t is 0.56. divided by minus 2 gives me an answer of minus 0.28 to 2 decimal places. Okay, so let's look at a natural log equation. Well, exactly the same rules are going to apply, just like logs. We're going to follow the same steps. So the first thing I'm going to do is, well, I want to bring these logs together, but I can't because of this 2 here. I can only bring a log and a log together. So I'm going to need to grab that 2 and put it up there as a power. Just like before, if I've got a natural log of this is equal to a natural log of this, they cancel, meaning this is equal to this. And again, finally, to finish my question, I'm not always writing anything, I'm just looking at my answer of 3, and I can't again take a log, natural or otherwise, of 0 or a negative number. It has to be positive. If x is 3, is this fine? Well, 3 take over 1 is 2. Natural log of 2 is totally fine, so that's my answer. So let's finish off with something that's not part of the course. It will crop up at advanced higher, but just a bit of background. The number e is 2.718. Why, though? What is important about it? Why does it get its own letter? Why do we use it? To understand that, you need to have a look at a few different exponential graphs. So here's roughly the graph of 2 to the power of x, and there's a graph of 4 to the power of x, and you see 4 gets much steeper. The bigger the number in general, the steeper it rises here, and the smaller the number, the more shallow it goes, whilst still being bigger than 1. Now, if you have a look, when the y value, or the fx value, the height of the graph gets very low, the gradient gets close to 0. In other words, when the y value is near 0, the gradient is also very, very flat, near 0. When the y value increases, going up here, so does the gradient. And somewhere in between here, there exists a graph where for every value, the y value is exactly equal to the gradient m, or in other words, in a curve, dy dx. Now, probably a nicer way of writing that is you get a function for which fx, the y value, is equal to f dash x dy dx. Now, the precise number in between 2 and 4 where this happens is at 2.718. So for fx equals e to the power of x, 2.718 dot 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 to the power of x. When you differentiate it, you also get e to the power of x. Every single other function, when you differentiate it, changes. X squared becomes 2x, cos x becomes minus sin x, except this one, when you differentiate it, it does not change. There's only one other function, which when you differentiate it, does not change. Can you have a think about what that is?